is C6H13NO, and it would have let's see, one double bond equivalent. The groupings that we see, well, we see a 3H over here. We know that that's a CH3, but we also have another 3H here and another 3H here, so that would indicate 3 CH3s. We have a 1H over here. That's going to be a CH because it's got multiple peaks on it. A 1H that is an NH or an OH will never have multiple peaks because they don't couple to the things next to them. And you can see here, for example, this OH here is a single peak, and even though it's next to a CH2, it doesn't see it because the multiplicity rules that we use really only apply to hydrogens on carbon atoms. So let's see, that's a CH. We've got a 2H over here, and that's going to be a CH2. So what have we got left? Well, we've got a carbon, we've got an oxygen, and we've got a double bond equivalent. So I'm going to go ahead and say that that's a C double bond O. You'll notice that C double bond N was not a possibility because that's not one of the pieces that we see here. And what that leaves us with is an N and an H, and that's going to be an NH. And that would match with the 1H broad being over here. So the main reason that I can say that it's not a C double bond N and an OH is because there is no choice for a C double bond N in these pieces. And generally speaking, in real life, when you're looking at these compounds, a C double bond O is going to be far more likely than a C double bond N because they're just far more common. So that should be all the pieces, and it is. And we can now go ahead and put these together. Now we can look at some of the evidence we have here. We have a CH and it has 6 peaks. That would indicate that the CH is adjacent to 5 hydrogens. That would indicate to me that the CH was next to a CH3 and a CH2. We know that the anchor goes down here, and we also know then that the CH can't be next to both the CH3s and the CH2 because then that CH would have 9 peaks, and we're only seeing 6 here, so we know that those must be somewhat apart. The CH2 here, if we're looking at that, the CH2 has 5 peaks. That would indicate that the CH2 is adjacent to 4 hydrogens. If we put it in this situation, that would be okay because we've got 3 hydrogens on this side and 1 hydrogen on the other. So we've got 5 peaks, and the CH2 is going to look okay there. The next thing we have to do is figure out what goes on with the CH3, the C double bond O, and the NH. Now, one thing I can tell you is that the CH3 here cannot be connected down here, and the reason for that is because the CH3 is a single peak. It's not next to a carbon that has hydrogens on it. So it must be apart from this grouping over here, which only leaves us to decide where the C double bond O and the NH goes. Now the C double bond O and the NH could be in this order, or it could be in this order. We can figure this out by looking at the correlation chart, where we notice that things connected to C double bond O's are generally to higher field than things with connected CHs connected to nitrogens. So if I've given a choice between 2 peaks, and one's a CH connected to an N, one's a CH connected to a C double bond O, generally the CH to the N is going to be the higher field than the CH connected to the C double bond O. So CHs connected to Ns are typically in the 3 range, and CHs connected to C double bond Os are typically in the 2.5 to 2 range. So I would be fairly confident in putting the NH next to the CH3 like this, and putting the C double bond O next to the CH, and you can see that that would lead us to that kind of typical grouping. The other thing I can tell you is that the NH doesn't couple with the CH3 and the CH3 doesn't couple with the NH for the reasoning that I gave you earlier, and that is that the multiplicity rules usually apply to carbons on hydrogens and hydrogens on carbons and not so much hydrogens on nitrogens or oxygen.